Yeah, I start by repeating some easy definitions. I think we used them, or I introduced them in the Thursday session, but I want to just repeat them officially for the lecture. So this is the following definition. We fix a finite dimensional vector space. And we fix a bilinear form. So say beta from V times V to, well, for this chapter somehow we said the field of scalars is always the complex numbers, or write C. And we suppose that the bilinear form is symmetric. And we choose some subset S of the vector space. Then we define this space, the orthogonal space to S. So that's the set of all vectors such that the value of the bilinear form, when I put the vector in the first place and an arbitrary vector from my set S in the second place, I always get 0. What's this? Orthogonal space. And then there was this notion of beta being non-degenerate. If the space orthogonal to the entire vector space is just the 0 vector space.
Is this a good opportunity
So let's make an example. So the first one, now actually the field is the real numbers, so it doesn't really fit with this definition, but I want to, this is the most best known example, and the vector space is just R3, and the bilinear form, say VW, is given by V1 W1 plus V2 W2 plus V3 W3. So the standard inner product. So if I fix any non-zero vector, what's the orthogonal space? Space of vectors orthogonal to this vector. Well, this is the plane through the origin, which has V as a normal vector. So what's the set of vectors orthogonal to every vector? Well, this is the intersection of all planes. well, of all planes through the origin. Well, and this is just the origin. So, as we all knew, the standard bilinear form on R3 is non-degenerate. Right, just another stupid example. V is an arbitrary vector space, and beta, the bilinear form, is 0. So the map which sends every pair of vectors to 0. Well, and say V is an arbitrary vector space, but not the 0 vector space. Yeah. Then what's the space of vectors orthogonal to V? Well, that's the space of vectors such that all beta V W vanish, but they all vanish. So this is the entire space again. So in this case, a vector space with this bilinear form is not, or this bilinear form then is not degenerate. So beta is degenerate. Oh, just one remark. Oh, I forgot to clean this board. Yeah, I think I said this also earlier. Any bilinear form say beta. So for this thing, it doesn't even need to be symmetric, but think of a symmetric one. This induces a linear map. Say capital phi beta from the vector space to its dual space, so the space of linear forms. Well, how? A vector must be sent to a linear form. Well, which linear form do I take? Just the linear form which sends another vector w to beta of vw. So I fix the first argument, and then this gives a linear form in the second argument. So this is a very natural construction, and I can interpret these definitions in terms of this map. So then this definition we only made for symmetrical beta. So if beta is symmetric, then we can define, or we have defined V orthogonal, the space of vectors orthogonal to all vectors, and this is just the kernel of this map phi beta, and this property of being non-degenerate just translates as phi beta being an isomorphism. So sometimes it's nice to think about this map phi beta. Yeah, anyway, so this is not very difficult. I just wanted to write everything on the board, say for the bracket. So now we're going to use this notion of non-degeneracy to characterize the semi-simple Lie algebras. So this is the following theorem. Again, as usual, L is a complex finite dimensional Lie algebra. Then we defined the killing form, a symmetric bilinear form on L, and we can find out whether L is semi-simple. And again, this means there is no non-trivial solvable ideal in L. And this is just equivalent to killing form being non-degenerate. Again, the killing form was, it associates with a pair x, y of elements of the Lie algebra, the trace of the composition adjoint map at x, adjoint map at y. So how do we prove this? Let's start with this direction. So we suppose that L is semi-simple. Well, and we define by I the set vectors orthogonal to the entire Lie algebra with respect to the killing form. And then, of course, because of the definition here, we have to show that I is 0. So how do we do this? In the exercise 6.1b, you have shown, or will maybe still show, that I is an ideal. So in fact, whenever I take an ideal and take the space of elements of the Lie algebra orthogonal to this ideal, I get another ideal. And here, of course, the entire Lie algebra is an ideal, so we can apply this statement of this exercise and obtain that I is an ideal. Let's consider the following elements. X, an element of the ideal. So the ideal is in particular a Lie subalgebra. So you can form the derived subalgebra generated by the commutators in I. And I take an element Y of the derived subalgebra. Now I want to apply this criterion for solvability we showed earlier with this very long proof. So, well, X is an element of I, Y is an element of the derived algebra, but in fact we don't even need to know that it's an element of the derived algebra. It's certainly just another element in the entire Lie algebra L. So what's the killing form of xy? So X was an I, and elements of I by definition are orthogonal to any other element of the Lie algebra. So even if I don't take into account that Y is an element of the derived subalgebra of I, But just by y being an element of the Lie algebra, I know that the killing form vanishes. So, and then this was theorem 4.5. This was the criterion for solvability. So I is solvable. Right, this was exactly the condition we had to prove. Whenever we picked an element x of the Lie algebra and an element y of the derived algebra, then the killing form should vanish. Right. So I is solvable. L was semi-simple. Again, that means that there are no non-trivial solvable ideals. L was solvable. I is solvable. I is an ideal. So I must be trivial. So we've seen that. So let's continue with the opposite direction. So now we suppose that the killing form is non-degenerate. And I want to do a proof by contradiction. So I suppose that L is not semi-simple. And I have to produce a contradiction out of this. So it's not semi-simple, so there is a non-trivial solvable ideal. Say I. Be a non-trivial solvable ideal. So what does it mean to be solvable? It contains its derived ideal and the second derived ideal and so on. And at some point I get the kth derived ideal, and then eventually I get 0, right? That's the definition of being solvable. And I suppose that k is the last non-zero, the last exponent such that I to the k is non-zero. So there is another exercise, 6.3. What was that about? This exercise says whenever we have an ideal in Lie algebra and we take its derived ideal, then this is still an ideal in the entire Lie algebra. And so by applying this, I is an ideal, so I prime is an ideal, then we apply it again, so I2 is an ideal, and so on. So we apply this repeatedly. So we conclude that IK is an ideal in the Lie algebra. Let's abbreviate this by capital A, so this is ik, and also A is abelian. Why? Just by definition, I prime is A prime is I to the k plus 1, and this is 0. So we found a non-trivial abelian ideal here in our Lie algebra. So A is non-trivial, so we fix an element. A non-zero element of A. And now there's the tricky part. For any element y of the Lie algebra, consider the following map phi. Well, this is a linear endomorphism of the Lie algebra, and obtained as the composition of the following maps: the adjoint map at A, the adjoint map at X, and the adjoint map at A. So each of these is an endomorphism of the Lie algebra, linear operator, so their composition is also. And we want to study this map, which is somehow defined ad hoc here. So I claim this is the zero map. Why? Well, as usual, I just take a test vector, y in L, and compute phi of y. And I have to show that this is 0. Well, I take y. First I apply at A. Then I apply at X. Then I apply at A again. So this is my result here. So recall A is an ideal. So this bracket is contained in A. Still, A is an ideal. So this bracket is contained in A. Sorry, maybe it's not well readable. So yeah, I said this bracket is contained in A because the left component is an element of A. Well, now from this second bracket, the right component is contained in A. So as A is an ideal still, this is contained in A. So now I have a bracket between two elements of A, because of course A is an element of A also from the beginning. And A was abelian, so this is 0. Okay. So somehow we defined this magic map and showed that that's just the 0 map. Why did we do this? Well, if phi is 0, then certainly if we compose phi with another copy of add x, so this is still a linear operator on the Lie algebra. Well, of course it's still 0 because the composition of a 0 map with something, and we can write this as follows. Altogether now we have at A, at X, at A, and then U at X. So we just write this as at A at X in parentheses to the 2. And this is also 0. And from this I claim that it follows that the trace of at A times at X is 0. Why is that so? Think about the Jordan canonical form of this composition. So this composition has the property that if I take the square, I get the 0 map. So in particular, this composition is nilpotent. So all the eigenvalues must be 0. If there was a non-zero eigenvalue, then the map couldn't be nilpotent. And what's the trace? That's the sum of all eigenvalues, but as all eigenvalues are 0, then the trace must be 0. And this again is by definition just the Killing form. So we took a non-zero element of A and took an arbitrary element X of the Lie algebra, and we showed that the Killing form of A and X vanishes. In other words, A is contained in L orthogonal. But for this direction, we supposed that the Killing form is non-degenerate, so L orthogonal is 0. So this is a contradiction, the contradiction we wanted. You're fine? Or you want me to go over it again, over the argument? No. Okay. Yeah, so we showed this very important theorem, criterion for seamless simplicity. So this will play a crucial role later. So K is non-degenerate. So somehow like an inner product, and we can use geometric intuition and geometric reasoning. But this will be a topic for later. Now let's do something else first. Recall what we said about this Jordan decomposition. If X is a linear map, so an element of GLV for some finite dimensional complex vector space V, then such an element has a unique Jordan decomposition. X equals D plus N, so an additive decomposition such that these properties hold, D is diagonalizable, N is nilpotent, and they commute. But of course, this only makes sense for this Lie algebra, because we were thinking about matrices, about linear Jordan canonical form for linear maps. So, but in fact, we can define an analogous decomposition for an element of an arbitrary semi-simple Lie algebra. Okay, and this will be a longer story. So I just announced the theorem first, but then we'll need a couple of lemmas before we can actually prove it. So L is a complex finite dimensional semi-simple Lie algebra. And X is an element of this abstract Lie algebra, not necessarily a linear Lie algebra. And then I claim there is a, again, unique decomposition into, say, D plus N. So now D and N are elements of this Lie algebra. Another additive decomposition, such that, maybe this is, in the book it's called abstract Jordan decomposition, but maybe the good term would be a universal Jordan decomposition, because it has the following property. For all representations of the Lie algebra, so representations, whenever I pick a representation, I can form this matrix phi of x. So this is just a linear operator now on this vector space. And I claim I get the Jordan decomposition of this matrix just by phi of d plus phi of n. So for any representation, I get a matrix. What's its Jordan decomposition? Well, I just take this one. So this is the Jordan decomposition of phi of x. So there's a very, very strong property. I can find this decomposition, and it works simultaneously for all representations of the Lie algebra. As I said, the proof will be done later. But I also already announced the strategy of the proof. It's a two-step thing. The first step is I don't consider all representation, but just the joint representation. If I only consider this one representation instead of the family of all possible representations, then this already, how did I put it? I don't know, gives rise to a unique decomposition x is d plus n. So if I don't impose this property for all representations, but just for the adjoint representation, then I will find such a decomposition, and it will already be uniquely determined. And then I show that this decomposition works for the other representations also. So the adjoint representation has a special role here in this proof. So for part one, we start with that, and we need the following tool. It's called derivations. It's a very stupid idea. Recall whenever you have two differentiable functions, say C1 on the line, then you have this famous product rule. Fg prime is f prime g plus g. What is f g prime? Here, your product rule. And so we take a very naive point of view and say, okay, derivation, so forming the derivative of a function. This is a linear operator on C1R, and it fulfills this rule. So this is the derivation, the usual analysis derivation. So we just say a derivation is a linear operator which fulfills this kind of rule. So in our context, this becomes the following. So L is a Lie algebra. And I define the set of all derivations of L, der L. So these are operators on L. So the Lie algebra now plays the role of the space of differentiable functions. And what's the condition? Well, okay, we have to generalize the product of, what will play the role of product of differentiable function? That will be the Lie bracket. So d x y, take bracket and apply this operator to the bracket. This should be the same thing as product, so the bracket of df, apply the operator to the first one, g plus f dg. So, and this rule is supposed to hold for all x, y elements of the Lie algebra. So this is a what did I say? Yeah, thanks. Yeah. Yeah, so I'd say it's a rather simple-minded definition, but it turns out to be actually useful. I wanted to write down the name. So this is the set of derivations. Yeah, let's do an example. This notion, so L is an arbitrary Lie algebra here, and we fix an element x of the Lie algebra. So we, I want to find the derivation, so such a linear operator that fulfills this product rule. So why not try add x? That's certainly an operator on L. So let's just quickly check it. I think we did the same calculations also several times, but now in this language it just looks a bit different. So let's check that. Take two arbitrary elements of the Lie algebra, and I apply, how do I start? I apply add, maybe x is already taken, so I take yz, add x, yz. So this is just x, y, z. So of course I take Jacobi identity at this point. So I have to take all the cyclic shifts: x, y, z, x, y, z. And so here I just take the anti-alternating property of the exterior bracket, so I can get rid of the minus if I write this as x, y, z. And here I take the I switch the factors of the inner brackets, so also by the Lie bracket being alternating, I get rid of the minus sign. So and I just notice that this is add x, y, and this is add x, z. So this is exactly what we want. D, dy z plus y dz. So so we already get a whole lot of derivations just by considering all operators of the form add x, wherever x is an element of the Lie algebra. well, I said we get a whole lot, but it's well, it depends on the Lie algebra, of course. For example, if the Lie algebra is a billion, then I don't get anything because the add maps are always 0. And on the other hand, every linear operator is a derivation. So, but still, we get some derivations in general by this construction. Yeah, so in fact, so as I said, this construction may be bad. For example, if L is a billion, then it doesn't really yield non-trivial examples because we only get the 0 operator. But if L is semi-simple, things will become better. Namely, then the set of derivations of L is just the set of operators of the form add x for x, an element of L. So in this special case, the example gives us every derivation. So this is really important. So why is this so? This inclusion we have just seen, right? Whenever we have an element of the form add x, then this will be a derivation. So this was our example. So so let's put it as follows. We have to show that at L is everything. To show that there are no further derivations we don't obtain by this construction. Okay, and this is again a slightly longer proof. So I start with the following claim. At L is an ideal in. Oh, in fact, I forgot to mention that there L is actually a Lie algebra. Maybe I put it in the exercise. And the new one. No, there's nothing about derivations. Okay, so sorry for this. So the set of derivations is, of course, contained in GL L. It consists of linear operators on the Lie algebra. And what's easy to check, that's immediate from the definition, is that this is a vector subspace of GLL. And what's also easy to check but not totally obvious, so this is a small exercise or a small lemma if you want, that this is actually a Lie subalgebra of GLL. So it's closed under commutator. If you have two derivations, compute the commutator, the thing you get will still fulfill this product rule. So this is a Lie algebra, a linear Lie algebra, sub-Lie algebra of GLL, and this will also certainly be a vector subspace, the space of all elements of all transformations of the form at X, where X is an element of L, and I claim it's actually an ideal. So how to show this? Of course, I fix an element of at L, so this is parameterized by an element of the Lie algebra, and an arbitrary derivation D of the Lie algebra, and I have to compute the commutator and show that it's still of the form at something. Yeah, so I have to compute the commutator, say, in this direction, D at X. And yeah, as usual, I pick a test element because this is a linear transformation, so it's easier not to, for the calculations, not to work with linear transformations, but just to apply them to an element of the Lie algebra. So, right, so the bracket here is the bracket from GLL, so this is just the commutator of operators. So this is just D at X, Y minus at X, D, Y. So, yeah, D, Y, and at X is applied then, so this is just this bracket. Minus at X dy. So what? Did I put somewhere my notes? And okay, yeah. So right, I put the. Let's do it more slowly. So this is d at X y minus at X dy, and now I wanted to write this in the bracket notation. So this is the first term, and here I get X dy. Right. So I know that d is a derivation. Let's continue over there. I know D is a derivation, so I just use the rule here for the first summand. So that's dx y plus x dy, and the second thing just stays, but then of course these cancel. So I'm left over with dx y. So this is just a fancy notation for add dx applied to y. Oh, well, this is the fancy notation for this bracket. And again, what did I want to show? I want to show I compute the commutator of d in at x and still get something which is contained in at L. Well, dx is whatever, but it's certainly an element of the Lie algebra. So a commutator is just add of something in the Lie algebra. So this shows that at L is an ideal. So we've finished the proof of our claim here. Next claim is that this add map, so this takes L to GLL, sort of linear operators on L, and this is injective, so 1-to-1. So how do we show that something is injective? Well, we take an element X in the kernel. And we have to show that X is 0. Well, X is in the kernel. That means at X is 0. That means all brackets X, Y vanish. At X is the 0 map, so when I apply it to an arbitrary element, I always get 0. So in particular, I take the one-dimensional vector space generated by X. When I take any element of this one-dimensional vector space and compute the bracket with any element of the Lie algebra, I get 0, which is of course contained in the vector space, so this is an ideal. And even more, well, if I compute the bracket of any two elements of this vector space, still I get 0. So this is an abelian ideal. In L. So the kernel is an abelian ideal. Well, but if it's an abelian ideal, then it's certainly a solvable ideal. I recall solvable means just if I compute this derived series prime, 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 then eventually I get 0. Well, if it's abelian, I just have to take the first derived subalgebra, 1, just prime it once, and I already get 0. So I found a solvable ideal here in this Lie algebra. But now the important thing is that L was semi-simple. So this must be the trivial vector space. So the generator must be 0. So we took an arbitrary element of the kernel, this map, and showed that it's 0. So the adjoint representation is injective or faithful, as people say, for some reasons in this context. Yeah. Yeah, what's the next step? Well, if it's injective, then the image of the adjoint map is isomorphic to the domain. Hence, this is semi-simple. Suppose that L is semi-simple. If the image is isomorphic, it's also semi-simple. now we can apply this theorem 4.9, first theorem from today, that the killing form, so I write, if there are several Lie algebras around, I write as a subject, as a subscript, the Lie algebra of which I'm considering the killing form here. So the killing form of the Lie algebra at L, so the image of the joint map, this is non-degenerate. Right? Just because this was this criterion, being semi-simple is actually equivalent to killing form being non-degenerate. So now we use a statement from the new exercise sheet I just produced, namely first exercise here. From this, we can conclude the following thing. Again, where are we? We want to. We know at L is a sub-Lie algebra of the Lie algebra of all derivations of L, and we want to show that we get everything. But at the moment, we don't know this, so in our imagination, this is a smaller. This is some sub-algebra of der L. So what we can do, we can take the killing form of the larger Lie algebra. This is unrestricted to at L times at L. So we just allow as arguments vectors, pairs of vectors contained in the smaller Lie algebra. And in this exercise, you'll show that this restriction of the killing form of the larger Lie algebra coincides with the killing form of the smaller. So actually it doesn't work with an arbitrary sub-Lie algebra, but as a first step we already showed that it's actually at L is an ideal in the Lie algebra of all derivations. So, and this is what you'll show in this exercise. Whenever the sub-algebra is also an ideal, then this equation holds. So the restriction from the killing form of the larger Lie algebra is just the killing form of the smaller Lie algebra. So they coincide, hence this restriction is also, of course, non-degenerate. Okay, very good. So now we are ready for the final approach. So the restriction of the killing form on the Lie algebra of derivations to at L is non-degenerate. That means the following. I don't find any vectors which are contained in at L and which are also orthogonal to all vectors in at L. So this orthogonality here is with respect to the killing form on the larger Lie algebra of derivations. Why? Because this is, by definition, the set of vectors which are orthogonal to all elements of at L, but by this property, at L itself doesn't contain any elements which are orthogonal to all elements of at L, right? So this intersection must be 0. So let's compute the following thing.
Okay, so that orthogonal space is taken in the bigger
Right.
space there L.
Right.
Derivation there L.
Right.
Yes?
Yes, exactly. So there is unfortunately.
It doesn't make sense.
Yeah. So, yeah, unfortunately, this is the usual notation. This is somehow bad. So one should do another subscript here. It's too complicated. So. So what do we get when we form the commutator of an element of at L and an element of at L orthogonal? So at L is an ideal. We showed this as the first step in our proof. Then the orthogonal space is also an ideal. Again, so this is the orthogonal space in der L, so in the larger Lie algebra. This is an ideal by exercise 6.1 or something. Yeah, 6.1b. It's the space of vectors orthogonal to an ideal, so it's an ideal itself. So whenever I form a bracket between those, of course, they are contained in both of them. I use the both ideal properties, but I just showed this is 0. So whenever I compute the commutator of an element of at L and an element orthogonal to at L, then I must get 0. Maybe I indicate. So let's consider a derivation which is orthogonal to all derivations of the form at x for x an element of the Lie algebra. So something here. So what we've just seen is for any element of the Lie algebra, the commutator will vanish. So this was what? Ah, okay. Now I see what I missed. In the very first part of this proof, when we showed that the set of all this set at L, so the set of all at X, where X is through the ideal, where L goes through the elements of the Lie algebra, we showed that this is an ideal just by explicitly computing commutators between an arbitrary derivation and an element of this form. And then we showed that this, we had to show that this commutator is again an element of the form add of something, some element of the Lie algebra. And we showed, in fact, it was, namely, it was the element add of dx. Dx is just obtained by application of this linear operator to this element. Aha. So, very good. So now we can continue, because we've shown for any element x of the Lie algebra, add of dx is 0. Well, but if add of dx is 0, because we already showed that add is injective, then dx is 0. And as we showed this for all elements of the Lie algebra, d itself is 0. Right. So this is C above. Computed this commutator in the first part of this proof at dx. Here by the last step, we know the commutator must be 0. And so at dx must be 0. As the second or third step, we showed that the adjoint map is injective. So dx itself must be 0. And as we computed this for any element of the Lie algebra, then the operator d must be 0. That means what we've actually shown is that the space, the orthogonal space to add L, contains only the 0 vector. Okay, and now there is a general formula. Dimension formula. This goes as follows. Whenever I take the dimension of some space, say at L, plus the dimension of its orthogonal space, in this case at L orthogonal, then this will be bound from below by the dimension of the total space. So again, the thing is, at this moment, we do not know anything about